In this video, we are going to learn about interpreting the behavior of accumulation function. But before we go into the accumulation function, let's look back into what you have learned during the first part of this module, which is the derivation. So we normally link between an fx, okay, to its derivative, so fx, and this is equal to f and x. Okay, this is the slope of the function. This is the slope of fx. Okay, for example, we have fx straight lines. This is the fx. We know here it goes up, meaning the slope is positive. It goes up, it's positive, so because the slope is from left to right, it goes up. So the f accent x here, because the okay, we see the slope from left to right is always constant. Okay, the slope here is this one, and at this point is this one, at this point is this one, and so on. So we know that fx is positive. Why we know it's positive? Because it goes up. So equal to, so fx is positive and fx is plus constant, for example. And conversely, if we have fx equal to, for example, this one, so this is our fx. From left to right, we know it is moved from it going down. So when it is going down, and the value is constant because it's straight line, so we know that in this case fx equal to a constant, but the constant is negative. Okay, the other way of seeing it is, how if I have a graph of fx like this one. So it goes up. It goes up mean so if this is the fx, so the f accent x will be, okay, more than 0 because it goes up. And you see that actually as it goes up, the slope is getting bigger. So this is the slope at this point, slope at this point, slope at this point. So we know that the apart from it's positive, it goes up, it's also increasing, so it's going up. So when fx increasing, so it means that it's concave up. So this one is concave up. So conversely, let's say if I have an fx, for example, going down this way, so this is my fx. So what I know is the f accent x, or the f accent, sorry, the f accent x then, or this one equal to fx. What I know is, because it's going down, okay, it's going down, it is less than 0, okay, and it is also increasing. Sorry, it's okay. The value decreasing. Okay, so decreasing. So for example, this is some value. Okay, I'll go with another color. We have some value here. We have a value here. We have a value here. So the value is negative because and it's bigger. So it's decreasing. So what does that mean? The consequences is, we know that if f accent x, or derivative of fx, is less than 0 and it is decreasing, we know that the shape of the curve is concave down. And we also have, for example, maximum. We have here, for example, here this is an fx, so we know that it is from left to right. Okay, so what happened here is, on the left it is a negative, fx is less than 0, and on the right it changed from, and at this point fx equal to 0. So sorry, this is fx. And to the right, so here we have fx more than 0. So we know that it is actually the minimum point. So extreme local minimum. This is local. So in this condition, we know that it is local minimum. And we have space here. So how to indicate, how to know that the shape of the curve, what will be the derivative of fx if it has the local maximum. So maximum is, we have a maximum point here. So on the left, we know here, so this is our fx. It goes from left to right. Okay, before this point, we know that here fx, it goes up, so this is more than 0. On the right side, we know here is fx less than 0. So from positive to negative, okay, and of course at this point fx then equal to 0, so it's crossing that point. I know that under this condition it has a local maximum. So you see here that we can link between the derivative of function and the shape of the initial function. Okay, there's an example here. So let's say we have fx here. This one is fx. So it's the derivation of gx. Gx is defined as integral from 0 to x ft dt. So what we know from the lab, so okay, what we know from here is that let's imagine what the function look like. Okay, we want okay, so for example here from negative 2 to 0, from negative 2 to 0, what will happen from negative 2 to 0? What I know here is the value is negative, so it must be decreasing. Okay, decreasing, and the value is the absolute value is so it's negative and it's decreasing as I go to the right. So I know the initial function will go. Okay, so this is the gx. Okay, so I know that it will go down of that. Okay, and it cross at 0. So here it must be local minimum. And it is so this we know fx here is less than 0, and it will go up. Okay, it will go up from this point. So this is the, okay, this is sorry, the drawing is not perfect. Now it will start from and this is at x equal to 0. So it's a minimum because it's from negative to positive, and when it's positive it goes up. It goes up and increasing. So increasing means it's concave up. So it concave up like this, concave up. Okay, until I think this is x equal to, at this point this is an x equal to 5. And then at that point it decreasing. So it keep going up and the value decreasing. So it's concave down. So it's concave down. So that's it. That's saying, sorry, it concave down, meaning that it goes there, and then at 10 it it changed from positive to negative. So at 10 it means that there is a local maximum. So and that's it. Probably this is at x equal to 10. Okay, x equal 10. So we see here, and then when the curve change from concave up, so this is a concave up to, at this point is concave down, we call this as inflection point. This one is called inflection point. And then here in this slide we got to summarize all of the things that we have observed before. So for here on the left, when f is changing sign from negative to positive, it is the g is at local minimum. Okay, now it going up and it is positive, so meaning that it's concave up, the graph going up, and then at this point the value is still positive, so meaning that it's still going up, but now the absolute value going down. So this means that at this point it is concave down, and then it goes down, and then at 10 there's a change in the sign from positive to negative, so we know that it is reaching the local maximum. So this summarize. So if f is positive on the interval of 0 to 10, it means that g must be increasing, is positive. Then we know what we know is f change its sign at x equal 10 and x equal 0. So from at 10 it's from positive to negative. This is wrong. This is supposed to be minimum. And then at x equal so that's correct. So that is actually maximum at x equal 10, and the one and at x equal 0 at this point, so it is from negative to positive, so it must be minimum. And then at the range of -2 to 5, -2 to 5 from this point to this point, f is increasing, so g is concave up, and then from at range from 5 to 13, 5 to 10, suppose f decreasing, so g is concave down. So, and we see that g change concavity at x equal 5 from so it reflects the inflection point. So from this video you should be able to imagine how, if you're given the derivative of a function, you should be able to imagine what will be the shape of the integral of the derivative.